Next, we're going to look at a series of reactions that together form what is called the enamine reaction. The enamine reaction is built from two reactions that work in sequence. In the first reaction, we form a substance called an enamine. In the second reaction, we then do an alkylation reaction of the enamine and then hydrolyze the product, is to change the structure of an aldehyde or ketone in a manner similar to that which occurs in the enolate alkylation. The first reaction, the enamine formation reaction, starts with an aldehyde or a ketone. It uses a secondary amine. A secondary amine is an amine that has two carbon groups attached and only one hydrogen. The carbon groups usually are the same, although they don't have to be. This is another Pram-type mechanism. It uses catalytic strong acid, such as sulfuric acid or PTSA. We've seen a similar reaction in our aldehydes and ketones chapter, but in that case, we used an amine that had only one carbon group. We call that a primary amine. In the reaction using the primary amine, we ended up with a carbon-nitrogen double bond. In the reaction using the secondary amine, we instead get a carbon-carbon double bond with a carbon single bond to a nitrogen amine. This, therefore, would be an alkene amine or enamine. Once we form the enamine, we can use it to react with an alkyl halide. It will do an SN2 reaction from the alpha carbon to become connected to the alkyl halide. And then we will hydrolyze the result, give us a carbonyl back. Therefore, if we compare the final product to the initial reactant, we can see that we have replaced an alpha hydrogen with the carbon group of our alkyl halide. This works for both aldehydes and ketones. In general, what we see is the more substituted enamine is usually preferred because it's like a double bond. The more substituted double bond will be more stable. This is going to give alkylation on the more substituted side of a ketone. Therefore, it's going to be similar to what we would get from a thermodynamic enolate. Here are two examples showing actual reaction conditions and the overall sequence of both reactions. We can see here we start with a ketone, in this case acetophenone, and we use this secondary amine. This secondary amine is called pyrrolidine, and it's very commonly used for this reaction. We use sulfuric acid, and allowing these to react, we get our initial enamine. You can see that the alpha carbon has become a CH2. It has lost a hydrogen effectively. We then allow it to react with an alkyl halide, in this case a primary alkyl halide, bromopropane, and we can see that we form a new bond from alpha to carbon 1 of the alkyl halide, and then we hydrolyze and we get the ketone back. So effectively, we've attached these three carbons to our original ketone. Here's another example using cyclohexanone. In this case, we're using another common secondary amine, morpholine. Morpholine plus PTSA forms this enamine. Morpholine is used very often because it's a little bit more polar, and so the enamine intermediates tend to be a little bit more soluble in polar solvents. Our alkyl halide in this case is benzyl bromide. We're going to get a bond between the alpha carbon of the enamine and the CH2, the benzyl bromide. That would be this bond. And then we're going to hydrolyze and get a C double bond O back. We're going to break the mechanism down into three parts, actually. In the first part, we're going to look at just the mechanism of the enamine formation. This is essentially a modified Pram mechanism. We start with the ketone. Our first step is to protonate the carbonyl oxygen. We then add the secondary amine. When it adds, it has both carbon groups plus the hydrogen attached. So the resulting molecule has 4 bonds to nitrogen and a positive formal charge on nitrogen. We then deprotonate the positively charged nitrogen in order to make it stable. So we have a P, an A, and an M step. Now what we're going to do is remove the OH. To do this, we protonate on the OH hydrogen. We then get essentially a water leaving group attached to the rest of the molecule. The water leaving group leaves, so we remove the water. That creates a carbocation, which has resonance. And the resonance looks like this, where the pair of electrons on the nitrogen come down and make a double bond. The nitrogen then, in this case, would have a positive formal charge, but it has no hydrogens available to be deprotonated, so it can't do a make stable step. Instead, then, we're going to have to remove a different hydrogen. The hydrogen we're going to remove is going to be the hydrogen on the alpha carbon adjacent to the carbocation. We can see it most clearly in this resonance structure. Base will come over, remove that hydrogen. The pair of electrons from the CH bond will move down toward the positive charge and form the ene double bond. This reaction has similarities to the final step of an E1 reaction. Remember, in an E1 reaction, we formed a carbocation, and then we deprotonated adjacent to the carbocation to form an alkene. The next mechanism we're going to look at is the mechanism of the alkylation. We're going to start with the enamine that we formed in mechanism 1. The initial enamine structure does not look like it would act like a nucleophile on the alpha carbon. To see the nucleophile nature, what we need to do is draw the resonance structure of the enamine, which we get by pushing the pair of electrons from the nitrogen toward the adjacent carbon and pushing the pair of electrons from the double bond out onto the alpha carbon. In this resonance structure, we can see that this alpha carbon has a lone pair and a negative charge, so it would act like a nucleophile. When we then put in an alkyl halide, that lone pair will come and do backside attack on the alkyl halide in an SN2 reaction, pushing out the leaving group and forming a new bond between the carbon group and the original alpha carbon. This product has a carbon-nitrogen double bond where the nitrogen has a positive charge. We're now going to hydrolyze the carbon-nitrogen double bond. We're going to do a heteroatom exchange, replacing the nitrogen with an oxygen. The mechanism of that hydrolysis is shown here, and this is essentially a PRAM mechanism. The only thing is that we don't start with a protonation step because the nitrogen already has a positive charge and it has no lone pair to be protonated. So we skip the P step, and our first step is instead an A step. The water nucleophile makes a bond to the C double bond N carbon, pushing a pair of electrons out of the way and forming this intermediate. The positively charged oxygen with two hydrogens attached is deprotonated to make it stable, and we get our first intermediate. Now we need to remove the nitrogen. We protonate the nitrogen, which now has a lone pair. It becomes a positively charged nitrogen, which is a much better leaving group. We then remove that nitrogen. Forming this carbocation-like species, which has resonance, where a pair of electrons comes from the oxygen to the carbocation, making a positively charged oxygen, which we can then make stable by deprotonating. The product looks like this. The oxygen is written upside down just to make room from the beginning. We can write it flipped over. We can see then that that is our ketone or aldehyde that we started with.